Hello everybody, my name is Chris Brady, author of the Boeing 737 Tech Guide and the Boeing 737 Tech Site, and this presentation is about the NGS story. So we'll be covering I'll start with an overview, then going on to accidents, flammability reduction, removal of ignition sources, center tank pump changes, fuel tank inerting, NGS on the 737, and a summary and timeline. As always, please do treat your company training and their manuals as the authoritative source of information. So by way of an overview, because I'm going to be covering the sort of overview and the where NGS came from, why it came about, rather than just looking at the system. To give some background, since 1959 there have been 18 fuel tank explosions on transport category aircraft. Now, of the many and various causes, they include lightning, wiring defects, heating of fuel vapours in the centre tank, and various other things. But they were the big ticket items. Now, following the TWA 800 accident, the FAA produced Special FAR 88 in 2001 and the Fuel Tank Flammability Reduction Rule in 2008, both of which mandated extensive safety improvements to the fuel systems. Now, as 737 pilots, we see the effects of this in changes to center tank pump design, the auto shutoff feature, and operation. There were numerous changes to SOPs a decade or so ago, and the introduction of NGS. Now, in this video I'll cover the background to these changes in more detail, the ensuing regulation, and of course the NGS system itself in some depth. So let's start with the accidents. The first ones were a Pan Am 707 at Elkton in 1963 and in 1976, and Iranian Air Force 747 at Madrid. Both of these aircraft were struck by lightning, and that caused an explosion of a wing tank. Both aircraft were destroyed with loss of all on board. Now, what they had in common, apart from being struck by lightning, was that they'd been fueled with a mixture of JP4 and Jet A. Now, JP4 has got a much lower flash point than Jet A and was prone to static buildup. And as a result of these and other accidents, it was phased out in the 1980s in favour of the more stable Jet A that we use today. And you can see the flammability envelope shown there on the bottom right hand side of the picture. Now, for those of you listening to this and question my use of the term Jet A as opposed to Jet A1, Jet A is mostly still used in the US, whereas the rest of the world we've kind of gone over to Jet A1. The difference in flammability, well, there is no difference in flammability. The flash point's the same, and as I say, all the flammability is the same. The only real difference, well, there are two main differences. The freezing point's about 7 degrees lower on Jet A1, and there's an anti-static additive in Jet A1 as well. Which again is for ignition reduction. So the first 737 explosion, and there have been two, was in November 1990, and it was a 737-300 operated by Philippine Airlines, and this was destroyed by a center tank explosion just after pushback, unfortunately with the loss of 8 lives. Now, there's been no formal report made public on this, but I've seen what the NTSB have said about it, and their summary is that essentially that the center tank was empty, and actually had been for a month or two, but probably contained fuel vapour from the evaporation of residual fuel caused by heating from the air conditioning packs, which are located directly beneath the tank. And these have been running for about 30 to 45 minutes prior to the accident in an outside air temperature of 35 degrees C. And it's thought that the ignition source was damaged wiring. Now in 1996, a Boeing 747 operating flight TWA 800 exploded shortly after takeoff, and that killed all 230 on board. Again, the packs had been running for several hours prior to pushback, and the explosion was in the center tank, which was empty. The NTSB determined that the probable cause of the accident was an explosion in the center wing fuel tank resulting from ignition of the flammable fuel air mixture in the tank. So that's even though this tank was empty. The source of the ignition energy for the explosion couldn't be determined with certainty, but of the source evaluated by the investigation, the most likely was a short circuit outside of the tank that allowed excessive voltage to enter it through electrical wiring associated with the fuel quantity indication system. And they thought that was the most likely because on the CVR, the crew were heard to observe and question erratic behaviour by one of the fuel gauges very shortly before the explosion. Now the NTSB in their report also concluded that flammability was avoidable, i.e. could be eliminated. Now that's quite a big statement, and I take slight issue with that because this was, these conclusions were issued. Well, the report actually took several years to produce. It was over 3 years, I think, between the incident and when the report was published. And I think that was probably, well, A, because of the depth of the investigation, and B, because of the implications in what they concluded and recommended. I'll say avoidable is quite a strong word because it's whether the technology made it avoidable at the time. And I will come on to that in the subsequent slides. They also recommended the development of inerting systems. As I've highlighted in red there, they said significant consideration should be given to the development of aircraft design modifications such as nitrogen inerting systems. So that was the NTSB quite clearly coming out in favour of reducing flammability and suggesting nitrogen inerting systems. Now it was back in these recommendations, as it says there, were issued to the FAA before this report was issued in December 1996. So that's how far back you can trace NGS in commercial aircraft. So let's talk about flammability reduction. In 1998, in response to the NTSB report into TWA 800, the FAA tasked the US Aviation Rulemaking and Advisory Committee, known as ARAC, to explore ways to reduce flammability in fuel tank systems. Because obviously the NTSB had said it was achievable, but there was, at the time the NTSB said that, there was no commercial NGS system. Now ARAC concluded that existing technology, which was onboard inert gas generation systems known as OBIGs, was not practical for commercial aviation because it was too heavy, expensive and unreliable. Now I should say that OBIGs existed in military aircraft, which of course are not operating commercially, and are also operating with fuels which are much more volatile than Jet A1. But ARAC looked into it and they concluded that it was too heavy, expensive and unreliable. Now in 2001 the FAA convened ARAC again for another look at the issue. And again, it was concluded that an OBIG system would reduce the flammability exposure to almost zero, but none of the design system concepts studied were found to be reasonably balanced by their incurred costs. And they went on to recommend that if a practical means of achieving a cost-beneficial fuel tank inerting system is found, then to come back and establish corresponding minimum flammability level and re-evaluate proposed regulatory texts and guidance materials accordingly. Now, this sounds a bit harsh to us now to say reasonably balanced by their incurred costs, i.e. bringing cost into it when lives are being lost. But just to play devil's advocate for a moment and explain some of the reasoning behind this, if you have a system that say weighs several tons, then that really eats into the payload, and if it's not particularly reliable, then what benefit is it? At the end of the day, aviation has to be commercially viable to exist. So it seems like a cold hard statement to say that that there's no cost beneficial fuel tank inerting system at the moment, but you have to set it in the context of what is practical. So the other side of the coin from reducing flammability is the removal of ignition sources. And although the NTSB had said that the best solution was to inert the tanks, both ARAC working groups had concluded that there was no commercially viable product available yet. So the FAA therefore continued in its efforts to eliminate ignition sources, which is the other side of the equation. And in May 2001, the Transport Aircraft Fuel Tank System Design Review and Flammability Reduction, the FTS rule was created. And whilst you may not have heard of that, what you probably have heard of is Special FAR 88, and this was huge. This had a really very, very large impact on commercial aviation. So this is or part of SFAR 88. Became effective, say, in June 2001, and it gave 18 months. It's quite a short time frame, really, for manufacturers to complete a fuel system safety review to eliminate ignition sources. Now, by system, they meant everything, the whole lot: tanks, pumps, quantity indication systems, lightning protection, wiring, everything. And it mandated three things. First was regulatory changes to ensure that ignition sources in fuel systems are prevented by design. So this is that all future designs don't have ignition sources. Secondly, changes to existing fuel systems to eliminate potential ignition sources identified by the safety analysis. So that's all current aircraft or previous aircraft. And then finally, to look at maintenance and inspection changes to ensure the continued airworthiness of fuel systems, i.e. that they continue to not have ignition sources. And you can see I've highlighted a couple of lines in SFR 88 up there saying to preclude the existence or development of ignition source. This subpara 1 down here talks about the ignition prevention requirements, which are these two FARs. And again, they're making reference to precluding the existence or development of an ignition source. So this was really quite big. Now, on the 737, things that were changed as a result of SFAR 88 include the following, and this is not an exhaustive list. These are just things that I'm aware of, and I'm sure there were many more, and probably quite a lot of nuances and things within these headings that I've put together. So there were things like rerouting of wiring, such as for lights, on the wingtips, away from the fuel tanks. Apparently, wiring for wingtip lights used to run through the fuel tanks. It no longer does. The installation of centre fuel tank hot shore protectors. Lightning protection bonds to fuel and surge tank access panels. They're those oval discs that you see under the wings. Centre tank auto shut-off pumps and master caution logic changes, which came in from May 2004, which I covered in the previous video on fuel. The addition of an isolator to motor-operated shut-off valves, spar valve actuators. Wing centre tank bundle insulation changes. Hot shore protector installations, fuel feed line bonding, fastener sealing and wire bundle support inspections, and all relays to have a ground fault interrupter feature, which is that box at the bottom shown there with the two red lights on it. So there were an enormous number of changes for the 737 and every other airliner as well as a result of this. Now, as a result of SFR ATR, what happened was, as the manufacturers did the safety analyses and found potential ignition sources, they reported them to the FAA along with rectification work, and the FAA would issue an AD, an airworthiness directive, mandating that work was done. And this is just one example of the dozens that were issued following SFAR 88, and this particular one was for what was this? The ground fault interrupter. But as I say, there were dozens of these, not only for the 737 but for all airliners. So just a quick reminder of the centre tank pump changes and why they came about. So on 3rd of March 2001, a 737-400 of Thai Airways was destroyed whilst parked at the gate due to an explosion in the centre tank. And one flight attendant was sadly killed in that explosion. Fortunately, the boarding hadn't commenced, so the aircraft was empty except for crew. They were just preparing the aircraft for service. Now, this accident bore a lot of similarities with the Philippine one, and also to an extent to the TWA one. The OAT was 36 degrees, the aircon packs had been on since the previous flight, and the flash point of the fuel was 40 degrees. The centre tank fuel pumps were running, as was found in the investigation. That's that upper right picture there showing the actual centre tank fuel pump switches from that aircraft. And it is known that the centre tank was empty of fuel at the time. And what happened on this one was, well, the probable cause was an explosion of the centre wing tank resulting from ignition of the flammable fuel air mixture in the tank. The source ignition energy of the explosion again couldn't be determined with certainty, but the most likely source was an explosion originating at the centre wing tank pump as a result of running the pump in the presence of metal shavings and a fuel air mixture. So the pump was deteriorating, probably from being run dry, and eventually deteriorated to such a point it started sparking, and that caused the ignition and the explosion. So 2 months after that Thai explosion, when preliminary findings became available, and folk had a good idea of what happened, the FAA issued this AD 2001-08-24 for the 737, and this added 3 AFM limitations restricting the use of centre tank pumps, and these limitations are still in force now, and I'm sure you're all familiar with them, and they're written there. So that was, as I say, restricting the use of centre tank pumps. Now, whilst those limitations were there, it was clearly felt that it would be better if the pumps would auto shut off just to, as an extra safety barrier. And Boeing and Honeywell, I think it was, developed these modified center tank fuel pumps, which automatically shut off after 15 seconds of continuous low output pressure. A retrofit for older aircraft has been available since 2009, and you can identify whether your aircraft has got the new pumps by looking at the P63 panel, and if you see auto shut off boost pumps, then you've got the new pumps on board. The master caution lights and fuel system enunciator logic was also changed to illuminate when either center tank fuel pump indicates a low pressure, and that used to be both. Okay, on to fuel tank inerting, because this really is the critical issue. And if we sort of look at the difference between inerting and ignition, the goal of SFR 88, if you recall, was to eliminate ignition sources. But the subsequent safety assessments made on systems revealed that there were more ignition sources than expected. Once you start looking for things, you start finding them. The NTSB have made this conclusion in their investigation of TW800, which was issued before SFAR 88, and they said that a fuel tank design and certification policy that relies solely on the elimination of all ignition sources, whilst accepting the existence of fuel tank flammability, is fundamentally flawed, because experience has demonstrated that all possible ignition sources cannot be predicted and reliably eliminated. Now, this was really seen as the NTSB taking a pop at the FAA for going down the route of SFAR 88. I'm not sure that was quite the case, but it certainly does look like a swipe at the FAA. I think they were just trying to be factual, and the FAA were doing their best because there wasn't a suitable NGS system available, so they needed to focus on ignition. And really, it's done us all a favour, because we've not only reduced flammability, but we've reduced ignition as well, and that has to be a good thing. Anyway, moving on. So again, talking about ignition versus flammability, for an explosion to happen, you need both an ignition source and the critical fuel-oxygen mix, i.e. flammability. Now, as the NTSB predicted, and the FAA found, there are a multitude of ignition sources, many of which can't be eliminated. Now, I've listed some there. You've got things like the tank units, compensators, densiometers, so they're all in the trying to gauge how much fuel's in the tank. Fuel pump arcing, burn through, and foreign object damage, like happened on the Thai 737. Lightning, which, as per the opening slide, brought down the Pan Am 707 and the Iranian 747. I mean, you will never ever eliminate lightning. That just can't be done. Electrostatic sparks, fuel quantity indication shorts, as brought down, or believed to have brought down TWA 800. Other wiring going through the tanks, improper maintenance, aging systems. Now, other wiring is what it was believed with the Philippine accident. So, and there are more ignition sources than that, but it only takes one of those combined with a flammable tank for an explosion to occur. Now, the cause of flammability: partially empty tanks, so you've got vapours in the tank, high ambient temperatures to boil off that fuel and make the vapours. The location and the use of packs, that's because the aircon packs are underneath the fuel tanks, and as they run, they generate heat, which is the same as having a high ambient temperature. Put the two together, and you really do start to get fuel vapours in the tank. With the fuel vapours and an ignition source, just one of that huge list of ignition sources, you will have an explosion. Now, whilst there are many aggregating factors to flammability, you can actually eliminate flammability by simply lowering the oxygen levels. I say simply, I mean this was what Arak found, that it wasn't actually that simple. But if you find a suitable inerting system, not only do you take away the flammability, you take away the possibility of an explosion, because you need both ignition and flammability. So it kind of doesn't matter if they're ignition sources. As long as you have no flammability in the tanks, you will not have an explosion. So that is the key to it. That is the key. So, following the Arak conclusions, a cheaper, more reliable to onboard inert gas generation system was sought, and that was ground-based inerting. Now, ground-based inerting has got no onboard system weight because the generation of nitrogen is done on the ground by a rig somewhere, or bought in tanks, and then it's pumped into the whichever tanks require it on the turnaround from a ground cart. So it's much like servicing tyres, I guess, where that's done with nitrogen bottles, only you're actually servicing the fuel tanks. So that was the only system which looked suitable at the time. So back in 2001, the FAA did research into ground-based inerting trials using a 737-700, and the document's there. And again, you can Google this and find it for yourself. It's public domain. And what they found was that it performed well with a couple of exceptions. Now, let me just start by explaining my little Mickey Mouse diagram of a fuel tank up there. So that is a fuel tank. You've got the typically straw-coloured Jet A1 at the bottom, and up at the top in the air gap, which is known as ullage in the correct parlance, you fill that void, that ullage, with nitrogen from your ground-based source, your nitrogen bottles or what have you. So that's how the tank looks on the ground after it's been serviced. The two problem areas that the FAA found on the flight tests were that, first of all, high fuel loads. As the consumption of fuel induced airflow into the vent started, it increased the ullage oxygen concentration because you're drawing in air from the outside, which is diluting the nitrogen that the tank had been charged with. So you end up, well, if you take the extreme view where you start with a full tank and end up with an almost empty tank, or an empty tank, you will end up with pretty much just air in there, not nitrogen. And air, of course, it has enough oxygen to be flammable. The second case was during the descent. Now, what happens during the descent is that the vent is there to equalize pressure, and that again works by drawing in outside air, which is relatively oxygen rich compared to nitrogen, and that of course created large and immediate increases in the ullage oxygen concentration. So GBI wasn't going to work. Interestingly, OBIGs, so an onboard gas generation system like NGS or what have you, would solve both of these problems, as the nitrogen-enriched air is continuously generated in flight to replenish the ullage rather than venting, which uses outside air. So again, it was they tried the GBI system, but basically found that it wasn't suitable for the job. Now, the other issue, in addition to the venting that I spoke about in the previous slide, is the oxygen solubility. Now, air readily dissolves into fuel, And in particular, oxygen dissolves more readily than nitrogen in fuel. So what you've actually got in the fuel is an oxygen-rich solution. Well, that's fine while it's in the fuel. Helps combustion. But after takeoff and during the climb, the reduction in air pressure causes that oxygen-rich air to bubble out of the fuel into the ullage. And again, I've written there my water bottle demo again. I think this is probably the third time in these series of videos I've referenced this. Again, but for those of you who've missed it, if you want to see this in action, before you take off, have a sealed bottle of water, and then in the climb, or at top of climb, open that bottle of water and you will see oxygen bubbles appear. Air bubbles appear around the sides of it, the inside of the bottle and in the water. And that's what happens in the fuel tank. As you climb, the partial pressure on the fuel reduces, and the oxygen is liberated out of the solution. Now this process obviously increases the oxygen concentration and hence the flammability in the fuel tank. So the point is, even if you started on the ground with a safe concentration of oxygen in the ullage, by the time you've climbed, it very likely will be unsafe. The second case is climbing with an almost full fuel tank, and here the problem is particularly severe because there's a lot of fuel, there's even more fuel, oxygen-rich fuel, and it's liberating the oxygen molecules into a much smaller space. So if you've got more oxygen going into a smaller space, the density of oxygen in that space will be far, far greater. So that's actually the most dangerous of all scenarios. Again, OBIG solves this problem as nitrogen enriched air is continuously fed into the tank ullage, keeping a head of pressure on the tank, so it's keeping the fuel partially pressurized, which will inhibit that liberation of oxygen, and any oxygen that is liberated will be flushed out as the nitrogen is introduced. So, what is a safe oxygen level? We know, or for those of you that don't, good pub quiz question, the normal oxygen level in air at mean sea level is 21%. So 21% of any box of air is actually oxygen. Now, research found that for Jet A1, not all of the oxygen has to be removed to provide adequate protection. And this was a huge breakthrough, because I think previously it had been thought that it did, and that is probably a throwback to military systems where the fuel was much more volatile or flammable. But certainly with Jet A1, what they found was that adequate inerting can be achieved with around about 12% oxygen at sea level, rising to 15.5% oxygen levels at 40,000 feet, and that is within the reach of technology. If you'd had to get oxygen levels down to single digits or approaching zero, that would have been very, very difficult to achieve. But only, well, halving the normal oxygen levels from 21% down to 12% or even 15 a bit percent at a cruise altitude, that is doable. So that is bringing the technology within reach for commercial aircraft. So you're starting to tick the boxes of lightweight, inexpensive and reliable, and this is starting to swing the balance for the cost benefit ratio that we spoke about earlier. So in 2008, the FAA issued its final rule. So I promise you, this is the last bit of legislation I'm going to show you. But this is the biggie. This is the important one, and it's the culmination of the others. And this takes a balanced approach of ignition prevention and reduce flammability to achieve fuel tank safety. So I've I've just cut and pasted the summary there, and if you just look at the first underlined part of highlighted there, so it says other required actions. So this to be done in combination with other required actions. The other required action is SFAR 88, ignition prevention. So as I say, it's harmonizing both here. And the part of highlighted in yellow says this final rule does not direct the adoption of a specific inerting technology, either by manufacturers or operators, but establishes a performance-based set of requirements that set acceptable flammability exposure values in tanks most prone to explosion. So basically for the 737 that means the center tank only, or require the installation of ignition mitigation means in an affected fuel tank. And it goes on to say that technology now provides a variety of commercially feasible methods to accomplish these vital safety objectives. So what it's saying is that you don't have to put NGS on your airframe, as long as you find a way of reducing flammability to safe levels, and we know what they are from the previous slide. It's 12%. And you only have to inert tanks which are at risk. Well, on the 737 it's the center tank, and probably the 747 as well, because they sit directly above the air compacts. So that's it. That's the big rule. And since 2008, that's what everybody's had to follow in whatever kind of airliner you operate. A Boeing, an Airbus, a Lockheed. It doesn't matter. That's the rule. So let's look more specifically at NGS on the 737. Finally, I can hear you saying, but I thought it was important to explain all the background to it and the lead up to it. First thing to say is that NGS on the 737 is actually a misnomer, and I suspect it is on all airliners, but I don't know. I only know the 737 system. Nitrogen is not generated. I know it says up there in big bold letters in the wheel well, nitrogen generation system. It isn't a nitrogen generation system. Oxygen is removed, and that leaves the air nitrogen enriched. I promise you, no nitrogen is generated during the process. The Honeywell NGS was certified by the FAA in Feb 2006 after over 1,000 hours of flight testing on a pair of 737 NGs, and aircraft have been provisioned with NGS since line number 1935, and it's been installed since line number 2620, which was May 2008 vintage. So any aircraft you're flying after May 2008 will have come with a factory installed working NGS system. The NGS requires no flight or ground crew action for normal system operation. Yay. So it's dead simple for us at the front. We just jump in and go. And if it's inoperative, it isn't required for dispatch. And I'll come on to that later on when I just show you the MEL requirements for this. But basically, long and the short of it is, if it doesn't work on the day, you can go without it. Alright, so overview. This photo here is a little tricky to kind of orientate yourself, but it's looking forward underneath the aircraft, underneath the belly of the aircraft. This is actually a very good engineering friend of mine kindly took this photo for me, and in doing so he had to remove about 60 fasteners to take this panel off. So my big thanks to him. He knows who he is. But so you can all see it, he took this panel off, and that's the NGS system. Everything in orange behind that panel is part of the NGS. Now that's the left ram air inlet mixing duct, and you can just about see on the left hand side of the photo there the left ram air inlet and the ducting for it in grey. So what happens is bleed air is first of all stripped of ozone, stripped of ozone, then it's cooled, filtered, Then much of the oxygen is removed and replaced by nitrogen to a level where the air will not support combustion, i.e. below 12%. The nitrogen-enriched air is then used to provide a header pressure for the center tank. So that's the big picture overview, and that's what it all looks like. So let me take you through the components step by step. Okay, first off, big scary schematic. Don't worry, I'm not going to go through this at all, other than to say that to point out where NGS is on the pneumatic schematic. It's off the left pneumatic duct. Left pneumatic manifold. So it's almost a bit of a red herring, it being located in the left ram air duct. The air source for NGS is not ram air, it is from the left pneumatic manifold. And it would be very easy to make that mistake because of where the system's located, but this is just to say it's bleed air. The minimum pneumatic duct pressure to ensure normal operation of the NGS, and by the way all of the other systems, is quoted as 18 psi. So you need at least that for the NGS to function. Okay, so start with the bleed air. Start at the beginning. The bleed air for the NGS, it's tapped off the manifold here. You can see that little T-junction coming down just right of centre of the picture. The air pressure and flow is regulated by the NGS controller, which is the computer brains of the NGS system, using the NGS pressure regulating and shut-off valve, and that's that valve, that first valve after where the air is tapped off. If an over-temperature or over-pressure occurs, that valve will close. The actual NGS system itself, which I'll come on to in a few slides, you know, where the magic happens, is very, very sensitive to the temperature and pressure of the air flowing through it. It needs to be just right for it to work as advertised. So there's a lot of temperature and pressure controlling goes on in this system. If the system should need to be deactivated, the engineers will manually close that valve there. So the on-off conditions, as we've already said, the NGS system is turned off using that pressure regulating and shut-off valve. Now, in addition to an over-temp or over-pressure condition, the system will be turned off automatically if any of the following occur. And these aren't actually in the FCOMs, but I've managed to extract this from maintenance documentation, and it is as follows. If either engine is shut down in flight, you'll lose NGS, and that is presumably to save bleed requirements, to save your bleed air. If fire or smoke detection in either the cargo or the main deck areas, so if there's any fire or smoke detection, then again it will shut off, and that again is so that you don't get the NGS system contaminated with smoke. As we'll come on to see, there's a lot of purification goes on for the air before it runs through the NGS system. If the left air conditioning pack is overheating, because again this is off the left hand side, so again if that's malfunctioning, we don't want any, let's say, bad air getting into the NGS system. If the center tank refueling valve is open, because otherwise you'd just be blowing nitrogen through the center tank and potentially, you know, back pressure in the Bowser, I guess. But if that valve's open at the other end, you know, you certainly won't be doing any useful work with the nitrogen. And finally, if the aircraft is on the ground and not in test mode. Now, I have to say I really do take issue with this last point. The reason I take issue with it is because the only two 737 center tank explosions that have occurred both occurred when the aircraft was on the ground. And here we are with with a perfectly functioning NGS system that does not operate on the ground. Why is that? I don't know. If anybody knows, please let me know. Write in, tell me, put me out of my misery, because it seems to me crazy that the system does not work on the ground. I get that you've got to have a bleed air source. Well, that would come from the APU on a turnaround, and I get that it would have to stop whilst fueling was in progress. But again, that facility is already there in point 4. So I have to say I'm baffled why NGS does not operate on the ground when to me, history would show that that is where it's most needed. But I'm sure there's a very good reason for it. I just don't know what it is, and I wish I did and I could share it with you. Anyway, that aside, the next stage is the catalytic converter for to remove ozone by converting it to oxygen. Ozone is really nasty stuff. It's it will oxidize almost anything it comes into contact with, and it's also quite toxic as well. So the ozone needs to be extracted, or in this case converted, before it passes through the air separation module, just to save damaging it. Okay, the next stage is the heat exchanger. As I've already mentioned, both the pressure and the temperature are very critical to the NGS process. So this uses ram air, or some ram air, to compress and cool the bleed air down to 71 degrees before going to the filter. The amount of cooling is controlled by modulating the amount of ram air used for cooling. So that's all very straightforward. The ram air exhaust is exhausted via the larger of these two holes, and the smaller one, which I'll mention later, but as we can see it there in the photo, it's actually the discharge for oxygen, carbon dioxide and water from the air separation module. So next time you're doing the walk around, and I don't know if you're on a check or something, and some training captain asks you what these holes are, you've now got the answer for him. It's ram air exhaust and exhaust for oxygen, carbon dioxide and water from the NGS system. Next stage along is the filter, and this removes solid and aerosol particles from the bleed air to prevent contamination of the air separation module. And you'll see in the next slide why the air has to be absolutely pure that goes into the air separation module. The filter's got a differential pressure switch to warn that the filter must be cleaned or replaced. That filter, though, according to Honeywell, should last for 12,000 hours, so a very long time on the wing there. Temperature protection, again, more temperature protection. It's got to this is the air going through the air separation module has got to be of the right temperature and the right pressure. So there are thermal switches, temperature sensors, and overtemp shut-off valve, which will shut off airflow to the air separation module if it overtemps. Okay, finally, this is it. This is where the magic happens. This is the air separation module, and what this does, as I've already said, it decreases the oxygen concentration and thereby increases the nitrogen concentration from the supply conditioned air. Any unwanted oxygen, carbon dioxide and water is discharged overboard through that green pipe there, which mates with the smaller of those two holes. So what's in the air separation module? It uses the hollow fibre membrane gas separation method as used in the industrial gas industry. The gases in the air are separated by selective permeation through thousands, I mean probably tens if not hundreds of thousands, each the thickness of a human hair. Now this is why the filtering is so essential. Each one of that, I mean, this is not drawn to scale. You've seen how big that that this air separation module is. You know, it must be, I don't know, a good 9 inches across, if not more. And if you're filling a cylinder with strands, membranes, the thickness of a human hair, you can barely imagine how many you can fit in. So what happens is this carefully controlled, conditioned air of just the right temperature and just the right pressure is fed through these membranes, and any gases that are small in molecular size, they permeate faster than the larger, less soluble gases. So what it does is it strips off oxygen, carbon dioxide and water from this air, and that is the stuff that's vented overboard, and the remaining air is effectively nitrogen enriched, and that flows out to your center tank. That's how it works. Now again, but one of the hurdles that had to be overcome was getting the oxygen concentration down, and that's done by effectively the pressure, the rate at which you pass the air through this air separation module. If you have too high an air pressure, the air will go through too quickly, and the oxygen won't have time or chance to permeate out and to be stripped out of the air. So it needs to flow through slowly enough for that selective permeation to occur. But obviously enough air needs to come through to replenish what is required in the center tank. So there's quite a balance to be struck. Okay, so next stage on is the high flow valve. Now there are two flows. The normal flow is the low flow, and that's what's used for climb and cruise. But the high flow valve opens in the descent to increase the flow of nitrogen enriched air to prevent ambient air coming in through the surge tank vent as the tanks pressurise in the descent. If you cast your mind back to those fuel tank diagrams I showed you, the descent was one of the critical periods as the air pressure tries to equalise. What you don't want is to let in ambient air, which is relatively oxygen rich. So this will go into high flow for the descent to generate more nitrogen enriched air to keep the tank levels safe. Again, after the air separation module, there's an oxygen sensor. This is a self-contained solid-state gas analyzer and pressure sensor, and it measures the oxygen content and absolute pressure from the air separation module. This data goes back to the NGS controller for status monitoring, and this only operates surprisingly once per flight leg. I don't know why so infrequently, but anyhow, that's what it does. Just once per flight leg, it takes a sample of the oxygen content and the pressure, and we'll use that information to either report a fault or serviceable. So the pipework continues and eventually enters the center tank from the left wheel well. So this photo is taken in the left wheel well, and you can see it yourself if you have a look around for it. There's at the junction where it goes into the tank there's a flame arrestor. Again, we covered those in the fuel video. Remember the Bunsen burner and gauze video demonstration. So there's a similar arrangement in there. I think it's a honeycomb actually on this one rather than a gauze, but nevertheless a flame arrestor is what it is, and a lightning shield down at the bottom of the photograph that you can see there. Uh, Last thing you want to do is introduce more risk and ignition sources inadvertently. So a lightning shield has been put on, which will deflect any lightning away from going into the fuel tank. The dielectric isolator hose is dielectric isolator. The normal application for this is to stop two dissimilar metals from contacting, and one starting to corrode or oxidize. But here it's kind of got the dual benefit that it's non-conductive. So again, no electric current or spark or ignition source or what have you should be able to enter the tank through this particular pipework. Okay, a little more about vents. Again, we've already covered these earlier on, but let's just look at the vents specifically with the NGS system. So as we know, all fuel tanks must be vented to allow air to replace the fuel used to prevent a vacuum forming. That we know. Now these vents serve both, also serve as overflow routes for excess fuel from overfueling, or if it's a full tank, from thermal expansion, or from sloshing about, manoeuvring on the ground. So the vents actually do have those two different purposes. Now the wing tanks vent from and overflow to the surge tanks. That's obvious, but what's perhaps less obvious is where the center tank vents to, and the center tank also vents and overflows to the surge tanks, which are out near the wingtips. There's no separate surge tank for the center tank, is what I'm saying. It just uses the existing wing tank surge tanks. Now, an NGS-equipped aircraft, there is a cross-vent check valve, and that makes sure that ambient air from the surge tank doesn't dilute the nitrogen concentration in the center tank, particularly as the aircraft descends. That valve's normally closed, but it will open to let fuel out of the center tank and into the surge tank if there is an overfill. So that's good. Now, there's also a float valve, just the same as you'd find, I don't know, in a toilet cistern or something. And that's at the highest point of the tank, and that will close automatically when the tank is full, and open when the fuel level decreases to let the nitrogen-rich air in. Because what you don't want is the NGS system, generating air and blowing it, straight into the fuel. It has to. It's there to for the ullage, not for the fuel. There's a backflow prevention check valve to prevent fuel flowing back into the NGS system. Again, this is for when the tank is full or expands due to heating, or say any other ground manoeuvres like an RTO or what have you, because we don't want to get fuel running back into the NGS. The NGS controller, which I mentioned earlier, it's the computer that controls everything, the brains of the system. You would have thought this would have been in E&E bay, but it actually isn't. For some reason, I'm not sure why, they put this in the air conditioning mix bay, which is located at the back of the forward hold. I don't actually have a photo of it to show you, but it's just a box. But you can, again, you've got one installed if you didn't notice on your walk around, by looking at the P18-2 panel, and you'll see nitrogen generator control and power circuit breakers. The controller also gives outputs to the operability indicator, which is the posh name for that unit in the wheel well, and the byte display unit, which I'll show you in a moment. Normal power source is DC bus 2, and alternate power source is the DC standby bus. Alright, the byte DU, this is like all byte units, it's used to interrogate the host computer, or the NGS controller in this case, to see if there's any faults in the system. And this, again, they were looking for somewhere to put this, and I think they really shied away from putting it where the NGS system is, because there are so many screws to take that panel off. They thought, right, we've got to make this somewhere accessible. As the unit isn't in the E&E bay, we got to put this somewhere handy. And they said, oh, I remember we've got some space in the air start unit hatch. Right, let's put it there. So there it is. So if you ever want to see it, then it's in the hatch where your air start plugs into. And that photo on the right is what it looks like. The operability indicator, this I'm sure you've all seen. The green operational light should be what you see. If you see the blue degraded light, then that is telling you that the system is serviceable but operating at a decreased capacity. So you do have some level of inerting. What level? I don't know. I'm not at all sure what the limits are on this, but there is something. If the amber in-op light is on, or indeed if no lights are displayed, then the unit itself is not serviceable. And engineers can use the byte displays unit that you saw on the previous slide to find the cause of the problem. Okay, I mentioned earlier we'd have a quick look at the MEL for this, and let's do so. This is an extract from the FAA's master MEL, so this should be valid for regardless of what operator you're with. So the FAA master MEL allows up to 10 flight days of operation with the NGS unserviceable, and by unserviceable we mean either amber or no lights. Now this is flight days. This is not calendar days, and I guess this has got perhaps an increased relevance with COVID times when aircraft are depending who you're flying with are not flying as much as they might have done. So again, this is not calendar days. This is 10 flight days. In degraded mode, you're allowed up to 10 calendar days, which oddly enough can be more limiting. But there is a slight subtlety here, which is the difference between an A level time limit and a C level time limit, is that there is provision to extend the C level time limit if necessary, and the C level one is the degraded mode, so the 10 calendar days could be extended. Anyway, I'm sure your airline will have it all quite clearly listed what it is and the time intervals involved. So just to summarize, NGS, where it came about from, the genesis of it, if you like. Starting over at the left, 1963, Pan Am 707, down by lightning, as was the Iranian 747 in 1976. Next event was 1990, when the Philippine 737 exploded just after pushback due to sense tank pumps. A suspected wiring fault, explosion in the sense tank. The next event was TWA 800 in July 96, which prompted the NTSB recommending nitrogen inerting as early as December 1996. ARAC 1 was produced in July 98. That basically said, can't do it, too expensive, it's too unreliable. And then fast forward to March 2001, and the Thai 737 explosion occurred. That prompted the centre tank pump AFM changes, and auto shut-off centre tank pumps appeared in 2004. Very shortly after the Thai explosion, a matter of months, ARAC 2 and SFAR 88 were issued. I suspect that was probably a coincidence because they're both big bodies of work, and I can't believe that they were started after March. But I'm sure they took on an increased significance following the Thai explosion, because it was exactly what the issues that they were dealing with. and that led to about 5 years of R&D developing NGS, which was eventually certified on the 737 in 2006, and the first NGS delivered 737 was in May 2008, just in time for the fuel tank final rule, which was issued in July 2008. So that's it. That's where it all came from and why we've got the system we have. As always, if you've enjoyed the video, please give it a like, subscribe to my channel if you haven't already done so, and share it and spread the word amongst your colleagues. Thanks very much for listening.